Hello everyone, and welcome back to a new episode of Silicon Zeros. I thought we would get back to the main track of the storyline. We've done a few asides, we did some multiplying and stuff. And next up is Fast 2-2, maybe? Not sure if that's 2 minus 2 or what, but now that you've built the simple parallel design, Sam, I need you to build one that can actually do math. Execute all instructions quickly, and try not to make it too messy. We've got a lot of new hires coming on, and they ain't used to the kind of designs you build. So, we have mset and addm are the only kinds of instructions we have to deal with. So let's go grab our collisions guy here, which did the same thing but only with msets, right? Yeah. So we can reuse most of this. I feel like having done collisions, Fast 2-2 shouldn't be that hard, right? Like, maybe I'm missing some subtle complexity, but I don't think so. We just have to do the same thing where the value that we write to here if we determine that the address we're writing to... Oh, it's a little trickier, isn't it? There's two kinds of races you can have now, I think. One race is when you're both writing to the same slot. In which case, what do you do? Well, I'm not sure. Because the second write could also depend on the first write having been applied. Right? Do we have any examples like that? Yeah, so dest is always what we're writing to. But here, after applying operation number 2, we need to say, oh, well, let's take advantage of that. We need to allow that write to happen. Use the result of that write in our second write. And that's fine. That's easy to do. We can just inspect the destination that it's writing to, compare it to the values that we're reading, and if it's equal to either of them, then instead of our reader, we'll take an input from this output selector here that's writing, or from, I guess, whatever we would be writing to memory. So that's easy enough, but the question is, like, there was another kind of conflict where two instructions are writing to the same place. Interestingly, it looks like we're not being asked to handle that anymore. We solved that problem already for, in the last puzzle. But it gets more complicated to solve it now, because... Well, actually, does it? I was going to say, if two instructions are writing to the same place, then we need to not let both writes happen. We need to let only the second write happen. But the second write might depend on the value in the first one having been applied, right? However, that's already handled by the case of two conflicting, or two dependent writes to different locations. You don't actually have to change your handling of conflicting writes to handle input dependencies, I think. So we want to leave that in, but we don't have to do anything special, I think. Okay, well, it's a little trickier than I thought it was going to be. We have a lot of time, though. 50 milliticks. Oh, divided by 2, though. What does that mean exactly? Yeah, I guess we can have our clock period be up to 50 because we're only spending half of it to write each instruction. Okay. So, everything up to here, we're clearly, like, leaving alone, right? We have to read these in. And we can't really stage things for the same reason that we had problems in the last one of these. We need the rights from the previous phase to have been applied already. Well, we could we not put a stage, like, in front of this stuff, if we wanted? Huh, I'm not sure. Maybe we could, but I don't think we have to, so I'm not going to worry about it. So what we need here is, okay, let's just get rid of these for the moment. Well, no, they're kind of nice to have. I'm just a little confused about what wires go where. So the destination, what we're writing to, is always going to go here. We always write to this destination. But if the... we need to make what we write, which previously was just coming from here, hard-coded, has to be attached to an operation selector. Right, that's what I grabbed. Did I grab an operation selector? Yes. If it's a memset, we read from source. Wait. Yes, source is an immediate value. We send that just here. And if it's an add M, we do something a little bit trickier where we read from source and then also read from target. And we will add those two things and have that be the value. Right, so that's how we're going to compute the... Let's see, is there some way I could make this a little nicer? Not really. Maybe it's better if I just do something like this. Line them up on top of each other. And then this sum gets routed back in a way that is not very satisfying, but whatever. So in this way, we've computed the right value that we want to write, and we know where to put it, which is to say either this destination or nil. Now, in this half, we want to do the same thing, but each of the inputs is going to have to take as an in addition to the reader, we're going to have to compare the address we just read from with the address that this guy wanted to write to. And if they're the same, then instead of reading from the memory reader thingy, we read from the output of this sum. Right? So let's just grab these guys and paste them here. I kind of want them upside down, don't I? Okay. So, based on our input, if it was a memset, then the value that we want to read is just the source. And where we're writing to is here. The memory slot we're writing to is definitely destination. But we need some more comparators. So, okay, let's fire these up before we worry about the comparators. These are reading from source and target. Definitely reading from those. It's just a question of whether we're going to use the output of this. And so what we need next is a comparator for each of these. Basically saying, is this... No, that's not right at all. Don't wire them up like that. Is the address that we're reading from, which in this case is source, equal to the address that this guy wanted to write to? Okay. And likewise here, is the address that this is reading from, the target, equal to the address that this guy was writing to? Now we have those comparators. And we have to use them as input selectors to our adders, I believe. So we have our one adder, I should say. Our one adder now needs two input selectors for it. Oh, that's an output selector. Go away. Input selectors on Q. Right, so this comparator is feeding this, and if it was 1, i.e. the values are the same, then we need to take our value as wherever this thing is here. Right? If they're the same, take the value from here, which is like this. Let me double check this. The address that it's writing to is always this one, regardless of whether it's mset or add. And the value it's writing is always this. Now, it might not actually write to that address because of this selector, but we're pulling from before the selector. So we say, yeah, okay, stop. So, whether, wait, these two inputs look like they're going to the same place. They both go to like here, but then one of them follows a line up like this. So if the destination of the first address was equal to the source of this address, then then we output a 1. And here, if the output is 1, then this thing, which was our source, instead of actually reading from our source register, here, let's do the 0 case. This one is our source register? Yeah. We read from what this guy wanted to write. And this adder needs a similar, or this input to the adder needs a similar thing. Based on whether the target of this address, or of this instruction, was equal to the destination of this one. If it was equal, then we'll just take this value here, and if it was not equal, then we'll take the value we read from memory. And now we have this adder, And all we have left to do is put an input selector onto this guy, which is whether we should use the result of this Rube Goldberg machine or just use the source. So where is that? Selectors are on 3Q? Memory slot is definitely destination, and we're definitely writing there, so we don't need a controller on that. Why can I not do that? Oh, it overlaps with this? Okay. So it's kind of interesting, isn't it? That this one needs a selector on its output memory slot? Oh, it needs selectors on both. We just couldn't... This one we couldn't put there next to it. Okay, fine. And the input select... No, we don't need an input selector. We need an op selector, right? Why do I not have any op selectors yet? Shouldn't this be... Shouldn't there be one somewhere? Oh. No, this is an op select. It just looks a little funny. And this is an op select as well. This is an input select, deciding whether to actually write or not. And what we're writing is fed by an op select, which is what we need. Okay. Op select is R. So, and we're feeding that input from here. What a monstrosity. This can't be the best way to do it. I feel like this part of, like, it looks like we're not being given any more collisions, so maybe I could save by getting rid of this stuff. I think it's just these two, basically, that are a problem. That we could perhaps remove in that way. But I'll leave them in because that's good for correctness. Anyway, so if this is a MSET, then we ignore all this garbage and we just do this source. If it's an add-m, we take the output of this sum. Right? In fact, let's do this. Okay, well, we're at 51. That's a little bit dangerous. Our two writer 3 from latch 7, latch 7, latch 7, and latch 7? What? What is that supposed to mean? Where is writer 3? 4? 3. So here's this path. And I mean, it does go all the way back to latch 7. I'm with you on that. I guess it's saying latch 7 because many times because there's multiple routes to latch 7 from here. Right? We depend on it in a couple of ways, maybe? I don't know. At any rate, 51 is slightly over budget, but we have 25 extra ticks, so I think it's actually fine, assuming that this is correct, which is a big assumption. Well, let's test 1. That's cool. So let's just step to the end of this this tick. Clock period, I guess. And what have we decided to do? We've decided to write a 1 into slot 10. That sounds pretty good. And a 2 into slot 11. Hard to argue with that. Okay. Cool. Now we have new inputs and everything's destabilized. I don't really see the point in waiting for the stabilization. We'll just skip over it and see what the result is. So this is the one with the conflict, right? We're setting in memory instruction 12, memory slot 12 to be 3. So where's our adder getting its values? We got a 3 from somewhere. That's pretty cool, right? We got it from here, which is here. The value we were trying to write is in fact being written because it's not the same thing the other instruction is writing. And furthermore, we're reading from it directly out of the adder, or the memory set thingy. rather than waiting for it to go through memory right. And so we get the 3, and we're now computing 1 plus 3 rather than 1 plus 2, which is what was there. So I think this is looking pretty good. Go fast. We've run the numbers, and it looks like the part cost is just too high with this approach. It seems like the parallel approach is a dead end. Doesn't help that we've been losing more and more employees lately. I swear, there's someone out there poaching my best people. Oh, the return of Jack. Well, hopefully you'll be able to salvage something from this, Sam. We still need those fast processors. So, we had the ideal number of ticks. The number of modules we used was 1 too many, huh? That's interesting, because I thought if we were going to be able to remove anything, it would be these 2 modules we could remove. Huh. Well, okay, so let's see what happens if we take these 2 out, right? And just wire this guy's destination directly into this memory slot. See if they've taken away that kind of data dependency. Delete. Just like that. I don't think that's gonna work. In fact, test 10 is when they finally give us an input like this, right? Yeah. So how does that happen? Yeah, we have collisions here, both writing to 55. Okay. And so if we skip to that when we're both writing to 55, we're writing a 3 and a 10 to 55, and it blows up. Right? Question mark. Oh, source. Writer 4 and writer 3 tried to write different values on the same tick. 203. Interesting. So maybe it does tell me what... At least it tells me where this came from. So that's sort of useful. Alright, so we just want to undo that. There we go. And now, when we run the test again, it completes successfully, I hope. So which one module could we remove, then? I feel like it's probably an op selector. We have a few more of those than it seems like we might need. So we need the 2 decoders, obviously. These 2 input selectors we need both of, because either the source or the target could have been written to by the previous instruction. So, okay, one interesting thing that we learned is that comparators with more than one input are an OR, right? Is any of these values equal to this one on the top? And so we could detect with a single comparator whether the previous instruction attempted to write to either our source or our target. Which, in a way, seems like a step forward, except that it doesn't actually help at all. We have to know which one of those things happened, so that we know which input to ignore, and which memory reader to ignore, and use the previous instruction instead. And indeed, it could be both. So you need 2 full bits of information, which means you need the 2 comparators, I think. Is there any way we could reuse one of the existing op selectors, maybe? Where does this guy even write to? Nowhere? I don't see this going anywhere. Yeah. it's just a dead piece. Okay, well that's what we were missing. Great. All right, now we made it down to the ID. So that was a nice, easy optimization to apply once I started looking in the right place. It might be nice if this game were to say, hey, you have modules that don't write to anywhere, you idiot. Like, maybe remove them or make them do something. In this case, it didn't affect correctness, just optimization, but I can imagine accidentally writing such a thing and believing an input is connected because, like, look at all these wires. How can I tell which ones don't go anywhere? It's a giant mess. So that might be a nice thing to add. I don't know. Interesting. Shift 1 is supposed to be easier, but still hard. Well, we'll take a look at it. We might get to it this episode, or we might just do an aside. Expecting Carol? She's busy. Board meeting again. I hear her parallel designs are too bulky. My advice, go back to linear designs, then split them up more than you've ever split them before. Get that clock period as low as possible. Put a 1 to the end of each value in memory fast. So what does this mean? Okay, so we want to multiply by 10 and add 1, basically. We have a single reader. Lots of writers and stuff. Instruction decoders we don't need. So we're given 18 ticks, and a multiplier takes 8. So I think that the obvious approach, which is the one with the lowest number of modules, might not be the one with the lowest number of ticks. That'll be interesting to try, see if there's a difference. So anyway, the obvious thing is to do what exactly? Where's my register? R. No, that's not R. R. Oh my god, throw all this garbage away, I'm so confused. Give me, please, a counter so I can read thingies. And then, at the end of it, a reader, which is this. And then immediately save that into a register, I suspect, is the answer here. We certainly don't want to multiply in that same tick. We just spent like 12 ticks reading something. We can't spend 8 more multiplying it. Doop. And then in this next tick, we're going to multiply, which is on R, this value by the number 10. And then save that in a register again, because we can't afford to put a writer in the same time slot as a multiply either. So let's just have another register, please. Ooh, actually, these should all have 2 values, because this is a latch. Get out of here. Stupid latch. Delete. Delete. I need a register, actually, because we need to store the address we're writing to as well. Like so. I think it'll be cleaner if I have the multiplier, like, up here. So that the relation between these things is a little more obvious. Now it's more clear that this 0 is being split. Okay. Now we've multiplied by 10. And you know what? We can fit and add 1 into this. It's going to be a relatively short cycle. So let's just add 1. That's a really strange wire routing. This way seems like it would should discourage crossing over. I don't know. He's done a lot on like how to route wires. I'm glad I don't have to route them myself. Let me tell you that. Having played Shenzhen IO, what a pain in the butt. I know that was part of the puzzle, but it wasn't my favorite part at all. Okay, and then finally, at the end of this, we can put just a writer. Like so. It kind of... I really ought to just do this in the right order to begin with, right? And then it's more clear anyway. Grab all this, put it on the bottom. Attach these two together and make sure we're storing... Let's see, this is the number we're adding. Put it here, actually, I guess. Or multiplying, whatever. Adding 1 to that and storing it here. This goes there. Yeah, okay. So I think that's the idea. And our clock cycle is just 15. Plenty low. And I think it works out just fine. Right? It's showing us test 1, which is either good news or bad news. So, I don't know. I should just, like... Just skip to the end of the thing, please. And what are we doing? We're putting a 0 and a 43 into this register to get ready to write them, or to do math on them. Next cycle, having done that, we're putting a 0 and a 431 here, so that in the next cycle we can write them. And then we write them. Great. So, this is all about just putting stages in, and since pretty much... How slow is our slowest stage? I'd like to look at that, actually. Okay, well, we did it perfectly, but... funny seeing Carol with those board guys all the time. She's earthy, old-fashioned. She's earthy, old-fashioned. I guess you need to put an emphasis on the she's, which wasn't so clear to me. They've got old money and modern morals. Since Carol got control, though, she's been crazy about pushing Zero-Com forward no matter what or who's in the way. Got the board eating from the palm of her hand. Makes me wonder, is she making them love her so she can use them? Or the other way around? I don't know. So, what actually is driving our slowest stage here? This. Reading the counter. Actually, this... Reading the counter is free, right? But reading an address from the counter and storing it into memory is our slowest stage, which is great news. Because we kind of have to do at least that much, right? 12 and 2 is 14. We also have an 8 and 5, which is 13. If that number were greater than 14, if this were our slowest step, we could split it up. We could put another register in between these two and add another stage, basically. But it only matters to... you only need to speed up the critical path, i.e. the slowest stage. All the other stages can be as slow as you want, as long as they're not the slowest stage. So adding another register here would make these stages faster, but it wouldn't actually help. In fact, it would make things worse, because we'd have the same total clock period. It would still be 15. But we'd have to wait one more clock period before we saw the outputs finally written. You know what? That might actually be an interesting demonstration. So if we run this test and say this, like go all the way to the end, we're at 135 ticks, right? And let's say that we said let's be as fast as we possibly can, and save the result of this multiplication by by putting another register in. Like so. And feed the time thingy from here. Send this guy up here. And feed that there. This is the same thing in terms of correctness, and this operation here is now each of these cycles is shorter, right? But it's actually made our overall progress slower. We still have the same clock cycle of 15, but I predict that it will take us exactly 15 more ticks to finish because we have to wait one more clock cycle before results start getting written. I'll just drag it over the end and we'll see. Yeah, exactly 15 ticks slower. And of course one module larger as well. So, just, I don't know, maybe an interesting lesson, maybe totally obvious, but something to say about how to optimize a multi-stage pipeline, right? You don't want to just make every stage as short as possible. If it's not the slowest stage, you want the stage to do as much as possible. But the shortest stage you want to, the longest stage you want to make as short as possible. All other stages you want to make as long as possible so that they can do the most stuff. Anyway, just an interesting aside, since I guess we're not actually working on asides this episode, but we did both of these this episode, I think, right? Anyway, I don't know. We're all done now, and in the next episode, I don't know, maybe we'll do more of this, maybe we'll do some asides, who knows. Either way, stay tuned, enjoy, etc. Thanks for watching, and I'll see you next time.